Assalamualaikum and greetings. In finishing the final year of degree, we as students are given a final year project to apply the engineering knowledge and skills. Today, I, Faridah Abdullah, will be presenting my final year project titled The Effect of Piston Geometry to Air Motion in 4-Stroke Diesel Engine. In the beginning of introduction, a background study conducted towards the main topic. In this, a 4-stroke diesel engine are the main focus because it uses compression ignition by using highly compressed air-fuel mixture. This mixture mixed by using airflow motion during the compression phase, but with the help of piston bowl. To improve diesel engine combustions, air and fuel need to be mixed in short time to fasten the fuel combustions. So, high velocity airflow and better air characteristics are needed to speed up the mixing process. The objective of this case study: first, to differentiate air motion by using three types of piston geometry. Next, to analyze the air motion by using CFD tools. The scope study are the simulation conducted by using ANSYS Fluence. Then, the airflow will be analyzed based on their velocity, characteristic vector, and TKE. And finally, the piston geometry that will be used are hemispherical, toroidal, and shower depth combustion chamber. In Chapter 2, literature review conducted towards the case study for better understanding. The piston bowl are hemispherical, toroidal, and shallow depth combustion chamber will be referred to a study conducted by Ganji and Jayachandar. Then, the diesel engine that will be used is Kirloskar TV1. In conclusion of literature review, TCC or toroidal shaped piston bowl is found to be develop better air motions that improve the air-fuel mixing and diesel engine combustion. In Chapter 3, I will be discussing about the method of conducting this study. This is flowchart to show the step process of this study. In short, ANSYS simulation conducted and the data will be plotted and analyzed. The geometry of piston bowl are designed by using design modeler of ANSYS software. Next, the piston bowl models goes through meshing process, which are inserting body size of 0.4 mm, inserting all triangle method, and also inflations. Next, in boundary condition, intake port is set as pressure inlet with 0 Pascal for natural aspired condition. The most important method in this simulation is dynamic mesh. Smoothing, remeshing, and layering is used for mesh deformation. Besides, in-cylinder parameter and valve profile also required for valve and piston motions. There are a few events that need to be addressed in dynamic mesh. In this, there are two. First, the valve motions, and next, the activation of intake port. The activation and deactivation intake port is important to avoid valve leakage. Lastly, in setup, it is highlighted air is incompressible ideal gas. And also in solution method, pressure velocity coupling scheme is coupled and the pressure term is standard. After conducting the simulation for piston motion during intake and compression phase, the in-cylinder flow development are studied based on their velocity and turbulent kinetic energy. A graph of average velocity magnitude versus carrying angle is plotted based on the data collected throughout the simulations. Based on it, it is found that HCC developed the highest velocity magnitude of 36.12 meter per second compared to other piston bowl. This peak occurred during the intake phase. By this finding, it is shown that HCC piston bowl can develop high air velocity flow during intake phase. Moreover, to investigate air motion for air-fuel mixing process during compression phase, a graph of maximum velocity magnitude versus crank angle plotted. The crank angle ranged from the condition of fully closed intake valve to the end of compression phase. Based on it, at 360 crank angle, it is observed that TCC model generate the highest velocity magnitude of 5.9 meter per second compared to the velocity of HCC model that is 1.7 meter per second, which is 3.7 times lower than TCC model. Due to the shape and reentrance curve of TCC model, there will be an increase of angular velocity and swirl velocity. This high velocity of air swirl generated by TCC model may helpful for air-fuel mixing process. Then, the observation towards the air motion is conducted during the compression phase and intake phase. During the intake phase, the air is moving downward and creating big vortex at the center of cylinder. During the compression phase, the air is moving upward as the piston moving to the top dead center. When the piston moving closer to the top dead center, the air fills the piston bowl curve and create strong swirl within it. That is important for the air-fuel mixing. Based on the observation, the TCC model generate the most productive of swirl circles. This display it is generating the high intensity of airflow swirling within the cylinder. Lastly, a graph of turbulent kinetic energy versus crank angle is plotted to view the TKE generation throughout the simulations. Why TKE? Based on the previous study, the TKE value can indicate the turbulent generation that is helpful for the combustions. Based on the graph, it is observed that TKE increase and peak during the closing of intake valve and decreasing afterwards. From the graph also is found that HCC piston bowl generate the maximum TKE value of 102 meter per second square during the intake phase. Next, it is found that TCC model generate the highest TKE value of 162 meter per second square compared to the other piston bowl. Overall, TCC model can generate TKE value higher than other piston, which is helpful for the combustions. In conclusion, by the end of this study, I successfully conducted the 2D simulation by using 3 types of piston in NC's fluence. I also be able to differentiate the air motion from each model. To conclude the findings, HCC model found to be develop high velocity during the intake phase. Meanwhile, TCC model generate high maximum velocity among the other piston bowl at the end of compressions. TCC model also generate high TKE value and also generate most swirl flow during the compression phase. Overall, there are significant difference of air motion due to the piston geometry. And based on the findings, it is concluded that TCC model generate the best air motion that is important and improve air-fuel mixing and diesel engine combustions. This is the ending of my presentation video. This study really inspired me to explore more the world of CFD simulation, especially engine simulations. This is not the end for me, perhaps a new beginnings. Thank you for your time and listening to my presentations.